All right. Wait, it's recording, right? Yes. All right. Good day, everyone. Most recent thing, we had a test last week, and everyone did very well. No issues, really. So congratulations. Test 2 is over. And to talk briefly about, well, first, does anyone have any questions from it? Or anything about electricity magnetism?
Is our final still on Mother's Day?
Good question.
That's not having to do with our test, that's just the first question.
That's fair. Sometimes you have to ask it when it's in your head or you forget it. Or that's just me. Okay, so yes, let's talk about upcoming events, including the exam. This week we'll operate pretty normally. We will have lecture, we will have lab. We're finally going to build the electric motors. Finally have all the stuff for it. Lecture will meet as normal today and Thursday. There will be a short homework assignment about what we cover in class this week. It'll be about sort of the greatest hits, the important things to know about waves, light and sound. It's going to be short because I want it to be due Friday night so that you don't technically have any assignments over the weekend or next week. So it'll be at least half as long. Sorry, at most half as long to facilitate it being wrapped up early. You okay with that?
You say that one more time?
Yes.
There will be a short homework assignment quiz this week about the waves and sound stuff we covered today and Thursday. Short because it's going to end early. It'll be due on Friday night so that it's done and over with and you don't have anything to do over the weekend other than rest and study. And rest. Do rest, please. None of us are getting enough sleep.
Are teachers invited to the campus-wide formal on Friday?
There's a what?
There's a campus-wide formal. You should bring Lulu.
Oh, well, going to the campus
We have,
wide
we
formal.
have 2 other things on Friday already. I didn't know about this.
I don't even know if professors are supposed to come. I just think that we would.
Maybe not since I wasn't told about it.
Us as students would let you ignore them.
Okay.
There's a cash bar.
I don't drink. Thank you,
Well, that
though.
won't help in persuading you then.
Okay.
Something you have to tell Dr. Gordon. Yes.
There will also be lab this week. Lab might be, there's an addition that I need to talk about when it comes to lab time this week. Do you guys remember at the start of Phys1510, you might have done a 30-minute Scantron multiple choice assessment. That's sort of like to gauge where students were coming into the physics department. Does that sound familiar?
Yes, absolutely.
There's one when you finish physics too. Help measure growth.
You're about to be very disappointed.
We do need to do that at some point, and I think having it during lab time, probably like we did last time, would make, at least that's how the department's done it in the past, having it during lab would be good, because then we just do it, it's done, and then we move on to the lab activity. We don't lose lecture time to it. So, for most lab sections this week, that will be the first thing we do. It's hard capped at 30 minutes, just fill in the Scantron, and that's it. And then we move on to the motors.
Can I come to Thursday lab?
Yes, I do not mind what section anyone attends this week. So lab this week will look like the brief, capped at 30 minutes Scantron assessment. It's not graded, but it is important data that we as a department need, so do come, be willing to do it. And then we'll move on to the motors. The only exception to that order of operations will be today's lab, because I'm getting my second COVID vaccine today, and I need to make sure I'm actually on time there. And to make sure that the lab gets done in its entirety, I just figured that I won't do the assessment for today. So Wednesday and Thursday, we'll do the 30-minute part at the beginning. And then, it's a little inconvenient, and I apologize. If you come to the Tuesday lab this week, I'm going to ask that you come next week just to do the 30-minute thing. There will be no other lab next week. I just need you to come in then to do the Scantron part.
And
pop in during one of the overlap times to do additional.
Yes, actually. If you want to come in a different day of this week to do it, that'd be fine too. It's locked at 30 minutes. As soon as 30 minutes are done, you're done, you leave.
Lady, we have to come in next week or sometime during lab this week to take a 30-minute exit exam.
Okay.
It's Scantron and it's ungraded. We just need the data. I do apologize for this inconvenience. It kind of got sprung on me because of the virus, we weren't really doing it, but then we didn't do it at the start. Words are hard, and I can't talk apparently. It's time for water.
Hey, you made it 13 minutes, buddy.
Thanks. Okay. So this week, lab, assessment during lab. Do please come for that at some point. It could be next Tuesday, it could be any other day this week if you have the 30 minutes at 1:30. Doesn't really matter to me as long as it gets done. Short homework assignment that'll be due Friday. Very, very short, just about waves. And then next week we will only meet on Tuesday. Since exams are coming up, I'm going to do what I usually do. On Brightspace, I'll upload practice questions, the list of chapters to be familiar with, the formulas that you will need to be able to know how to use. We will also be talking about that this week and next Tuesday as well. So this week and next Tuesday is waves and then exam review. After that meeting next Tuesday, the class portion itself will be over and then the exam season will start. Yes, this lecture's official exam time, I think, is on Mother's Day, which I don't think anyone thought that was a good idea. But since the exam is over WebAssign anyway, I'm going to use the same policy we've been doing. It will open up at the start of exam season, and you just have to pick a 6-hour window in which to take it.
Do you know what day it'll open?
Well, exams start
The 7th?
Friday the 7th, so it'll open then and it'll close the Wednesday after. Or the Tuesday. It'll close just shy of a week after. So, no, actually, you don't necessarily have to do it on Mother's Day. And you don't have to come into the building that day either.
That is an important caveat.
That has been a whole lot of information. How do you guys feel, and do you have any questions?
So our exams on WebAssign?
Yes.
Just clarifying that, I know you already said that.
Yes. It'll similar format to as before. Put your answers into the WebAssign, send me your work, and more points than it is graded out of. It'd be 210 points. It'd be graded out of 200.
I just hope it doesn't remind me of Phys1510 kind of.
Well, it'll be about different things, even though some of the foundational stuff is the same.
It's over everything we've learned this semester.
Mm-hmm. Including anything we talk about this week, waves and such.
So, Prof, what is a wave?
Great question.
Nope, this is slide 1 or else I'm going to let you do here.
It's actually slide 3, but you can pick which one shows up first. When an English-speaking American first says or hears the word wave, where's the first place, honest answer, your mind goes?
Ocean.
All right, very good.
The ocean. Yes.
Okay, the ocean and this, both technically count. Both count, neither are wrong. I'm gonna go with ocean for the time being though. Ocean waves are traveling energy. With all waves, energy is going from some place to some other place. And in the case of the ocean, you see that energy traveling by the water moving. The water has kinetic energy. That kinetic energy moves from further out at sea towards the coastline. It's important to note, though, that for all waves, the energy is what's traveling, not the material the wave is traveling through. In the case of the ocean, waves originate or can originate pretty far out. There's wind, there's rotation of the planet beneath the water. There's a lot of things out at sea that cause the water to start moving and cause waves to start moving towards the coastline. But does all that water out there, all that water, move towards the coast? No. The entire sea does not come towards the coastline with every single wave. The water moves as energy travels through it. All waves, doesn't matter what type, we're going to talk about a few, but all of them have the one thing in common: the wave itself is just traveling energy. Some of those waves travel through a physical medium. In the case of ocean waves, it's traveling through the medium of the water. In the case of sound waves, it travels through the air. In the case of seismic waves, it travels through the earth itself. Those are all just mediums that the energy of the wave travels through itself. I forgot to raid the closet for everything I was going to be doing today. I am going to grab a few more demonstrative things. I really like the waves chapter because there's just more cool stuff that I can physically bring out of here to actually use. So, one sec.
Okay.
I was not. Coffee is burnt.
Okay. Can I get someone to... Is this more than one? Yep. Can I get someone to hold the other end of this?
I can do that.
Thank you. I'm going to stretch from you to the other side of the board so that it's on camera. Thank you. So, this is a physical medium that waves can travel through. I'm going to make a wave.
You're right.
No.
Y'all ain't feel it.
Notice, as I do that, I'm putting kinetic energy, or I guess elastic energy, into the spring, and that energy is what travels through its length. The coils over here don't end up down there. So the water that makes up the wave in the middle of the ocean, that water does not actually end up at the coastline. Only the energy goes from point A to point B.
Question.
Answer.
When we're talking about waves in the ocean, on the shoreline, when they break onto the shore, you can physically see the water moving.
You are right. The medium does physically move. When I do this, you can see the slinky move. So as the energy travels through a specific part of the medium, it will move. It will oscillate in the same axis as the wave travels. In the case of the ocean specifically, the water might even rock back and forth, but it doesn't travel the full length of the wave. The coils on this end will go up and down. They might even rock back and forth a little bit, but they don't go all the way down. Just like how all the water in the ocean doesn't rush towards the coastline, and like how the water that does break onto the sand does go back. Similarly, sound waves are kind of an example where sound waves are an example that show that it doesn't move, because if it did, it would be disastrous. When I speak, I'm putting kinetic energy into the air, and the air starts vibrating. And that vibration, the ripple, is what travels to your eardrum. But it's only the energy that travels. if the air next to my throat traveled to your ear, I'd create a typhoon every time I talked.
That sounds pretty dangerous.
Yes.
A typhoon beating a hurricane.
I'd at least scream gale force winds. The air molecules next to my mouth do not travel to your ear. Only the wave does.
So it's like the air molecule here just says, okay, I'm just gonna pass this on to the next guy.
Yes, okay, actually, you know what? It's like doing the wave at a stadium. When the wave passes by a group of people, that group of people will stand up, raise their hands, and then it'll keep traveling down, right? You familiar with this? The individual person in their seat does move, but they don't travel with the wave. They return to their seat. But the energy keeps going.
I understand that in like this situation, but like when you're talking, like how are like the atoms or molecules like passing energy to each other?
Collisions.
So when they run into each other, one of them just loses it while the other gains it.
Mm-hmm.
Okay.
The molecules right next to my throat, like my throat physically shakes, so my throat collides with the air molecules. Those first molecules hit the next set, transfer the energy. Those next ones hit the next set, transfer the energy, and it's just a continued series of collisions. Additionally, while I have the slinky set up, zoom tight, we'll talk more about this later, but if a wave travels through a specific medium, so that's just the physical material that the wave travels through, that wave's speed will be capped based on that medium. Doesn't matter how much I pluck the slinky, the waves move at the same speed. The only way to change the wave speed is to change the medium that the waves are traveling through. If you could stay put, I'm just going to make the slinky taut. I've changed the medium's properties by changing how taut it is. There's now fewer rungs between their hands. The medium and the type of wave determines its speed. Which is why you may have heard the fact that sound is faster in water. Thank you. We might come back to this later.
That thing felt violent in my hands. That thing felt violent.
Sorry. Okay. Let's back up a little bit and start defining a few terms that are going to keep coming up. I'm going to refer to the term oscillate pretty frequently. Has anyone not heard that word before?
I think we're good.
Okay. So, oscillation, vibration, it's just repeated movement back and forth. A wave's amplitude is basically its physical size. Oh, I wrote physics instead of physical. It tells you how much energy the wave has. In terms of a slinky wave or an ocean wave, amplitude is its physical height, how tall it is over the baseline. For sound waves, uniquely, amplitude can refer to how loud they are. Not necessarily their pitch, just their volume.
This pitch is the next word there, okay?
Yes, for sound waves, and also light, frequency determines what pitch you hear and also what color you see. Frequency refers to how frequently something occurs. You can use it for terms other than just wave dissection, but in terms of waves, a frequency refers to how many times the wave completes a full oscillation every second. In previous physics classes, you may have used the term period of oscillation. a big capital T to represent the time it takes for one event to occur. Frequency is the inverse of that. It's events per second instead of seconds per event.
I'm sorry, can you say that again?
Yes. Frequency is a measure of how often something occurs every second. In the case of waves, it's how many times the wave in question completes a full oscillation every second. If I was to draw the stereotypical waveform,
I meant to repeat the part about the period is the amount of time.
oh, yes. Period of oscillation is, or the period in general, is the time it takes for a specific event to occur. You were watching a clock and you kept count of how many seconds it took for the, I don't know what the term is, for the hanging part of the grandfather clock to go back and forth, the pendulum. The time it took to swing back and forth would be the period, how long it took that one event to occur. Frequency is the inverse of that. This is events per second. If you were listening to a 30 hertz sound wave, that means that you would be hit by 30 full wavelengths every single second. How does that work for everybody? Does that not work for anyone, these descriptions? Do you have any specific questions or issues?
So how does, like that picture that you had on there with the colors?
Yes.
How is that a wave?
This is something I drew to describe an echo to the other lecture.
Okay.
So the red and the purple is not something I mentioned to you guys yet.
Okay.
This is relevant though. This sinusoidal shape is what most people think of as a waveform. And this is useful for defining what one whole wave is. Because if you have a wave or any sort of oscillation, the object in question has to vibrate from one point to a second extreme and then back to the first point in order for it to be repeated harmonic movement. For this waveform, if we were to start, say, looking here, the wave shakes down, then up, and then back to the same original point, falling at the median. That physical length from point A to point B is the wave length. It's the physical length of one whole wave. This chunk right here is one full oscillation, one whole entire wave. And so if you knew the frequency of that wave, you would know how many times this whole wave pattern passes every single second. Wavelength being the last term up here, it's just, again, the physical length of a single wave of the vibration. How do you guys feel? Okay. Faces are harder to read at this particular moment in history. Okay. So back where we were before. Waves are just traveling energy. The energy takes the form of a movement in some sort of object or field, and that movement transfers energy from point A to point B. The energy is what travels, but the medium does not. We are going to talk about different types of waves. There are similarities and there are differences. All waves have, like the 4 terms on the previous slide, all waves have those 4 things. All waves share those in common. What they differ in a few ways. One of the divisions between wave types is in the form of is the wave mechanical or electromagnetic? Pretty much every wave that you have seen, like if you see an object oscillating, it's probably been a mechanical wave. Mechanical waves are called mechanical waves because they are traveling mechanical energy, which usually by necessity means it's traveling kinetic energy. Because a physical medium has to move for that wave to travel. Anything that you have felt or seen moving or seen oscillating has been due to a mechanical wave. Yes?
What's that key word? At the very beginning.
Traveling? Yes, mechanical waves are themselves mechanical kinetic energy that is moving from point A to point B. And in order for that energy to move, it has to travel through some physical material. Ocean waves being the first example. There's kinetic energy out at sea. It travels through the water to get to the coastline. The water is the physical medium that the wave travels through.
Does physical medium, what's that last line there?
Has to move. It has to move through a physical medium, and that medium itself has to be capable of vibrating. Granted, most subatomic particles can vibrate, so most physical mediums will suffice. As long as a wave has an object, no matter what state of matter, it should be able to propagate in some way, shape, or form. The classical mechanical wave examples include ocean waves, sound waves, and seismic waves. Kind of a combination of land, sea, and sky. In all 3 of those examples, and a lot of others besides, these are just the classic ones, some physical material has to be shaking for energy to be able to travel through it. Seismic waves, the literal ground is shaking, and energy goes from the San Andreas Fault to Sacramento. Sound waves, energy from my vibrating throat travels through the air to hit your eardrum. Ocean, well, we've been saying all class period. But this includes any physical vibration through any physical object, regardless of the state of matter. These, so far, are all distinct from the other major wave type, electromagnetic. Have you ever thought much about what light is or how it gets to Earth from the sun? Well, good news.
You have.
I have. the previous wave types all needed a physical medium in order to be able to travel. You heard the sort of the movie line, "No one can hear you scream in space." It's because there's no air in space for the sound to travel through, which is shouldn't be a novel concept for you guys. And yet light can still travel through space because it doesn't need a medium. It is itself a very different type of thing to mechanical wave-like sound. It's still a wave. It has wave properties. It has all the wave parts about itself that we defined earlier, but it's made of something else. Sorry.
How is there no medium in space?
Space itself is not truly empty, I will admit. There's obviously rocks and planets floating everywhere, and stars, and nebula, and gases, and comets. But if you were to just zoom in on a particular region of space that we would call empty, there's a very, very, very thin amount of particles there. Like there's gas molecules, there's dust particles from everything else that's passed through that region of space. But space itself, like the region of, like the universe is just so big that all those particles have become so far out, it's functionally a perfect vacuum. All the dust, all the individual pieces of dust are just nowhere near each other, so it's just functionally empty. So I guess in theory, if like you were able to get those like those tiny pieces of dust to eventually hit each other, you could maybe get sounds to propagate through space if it was the loudest thing ever and you were willing to wait 8 million years. But there is not a measurable, meaningful medium for sound to propagate through space. Light, however, can because it doesn't need a physical medium. Light can travel through a physical medium. In fact, every photon you've ever seen, any piece of light that has ever entered your eye, has done so through a medium, because most humans have only ever seen through air or through water, but it doesn't need a medium. So light is an electromagnetic wave, so called because it's literally made of electricity and magnetism.
Things I hate.
Yes, that's fair. Light, I've been saying for weeks that magnets are weird. So is light. For as long as, those two things in conjunction have been causing scientists headaches for ever, frankly. Like the nature of light is historically problematic. Probably more famously so than magnetism, actually, at least by itself. As we currently understand light, a single, it's not really a particle, but a single packet of light, a single photon, is made of one oscillating E field, represented in blue, traveling in conjunction with a B field, represented in red, that is oscillating perpendicularly to the E field. So they're kind of doing this, but they're both moving forwards together. One of them sort of leashes the other and keeps them together at one, moving together as one unified entity. And that's part of the hard explanation for what light is. The easiest answer is it's just energy. It's pure energy that was emitted by something, and it's going to keep going until it hits something else and becomes absorbed by it, and then that object now has the energy.
So it doesn't stop.
It won't stop until stopped. The reason that we can see all the stars out there is because they made light, and it keeps traveling until it hits us. That said, this weird electromagnetic nature of light does explain why only certain things produce photons. Like stars make light because they're super hot, they're super charged, and they're constantly vibrating electrical particles, create these fields, and then those fields travel outwards. We kind of have to replicate that in these light bulbs. We charge up plasma. Plasma is inherently charged and vibrating. It creates the same fields and shoots them out as light. And because it is simply self-contained B fields and E fields, it doesn't need a medium like sound does, so it can freely travel through the void of space. So, no medium required. And frankly, light is not the only type. Light is a member of a larger electromagnetic family, which includes radio, micro, infrared, visible light,
So the electromagnetic spectrum.
ultraviolet, X-rays, gamma rays. Every part of the electromagnetic spectrum is the same thing that light is. This weird vibrating E field, B field situation. They're all physically made of that same thing. All that's different is their frequency and therefore how they interact with matter. So these, they're all off on their own. They're weird alien cousins together. Anything that's physically moving, though, is a normal mechanical wave. Questions so far?
That makes you feel uncomfortable. Not gonna do that.
Of this?
Not like that. I guess it makes sense then. Well, it's useful.
Makes you uncomfortable, though?
Like just move in both directions.
Light is a three-dimensional thing because it's like this photon here is traveling in the x-axis, but its E field oscillates in the y and its B field oscillates in the z. Light is a fully three-dimensional construct as we currently understand it. Sorry, taking a quick break from my throat and my vocal cords. How you guys feeling? Tired? Yeah, me too.
What time is your second vaccine appointment?
I need to be there before. I need to be there by 3:30.
We can make that.
Where is it?
The Lawrence County Hospital grounds, basically. There's a DHEC facility behind the hospital. Which I had to find out was DHEC and not the hospital itself because I had to call to double check when I could come in. Call the hospital and said, no, we have nothing to do with that. Bye.
Nice.
So I had to
That's
Zoom.
where I got tested
Oops.
at the DHEC.
Oh, at the DHEC place? Okay. Yeah, I had to find out that was DHEC by zooming in on the map where I went last time,
Yeah.
figuring out what what is on that plot
Well,
of
it
land.
routed me to like the old folks home across the street or whatever it is. Yeah.
Know
That's
about
not
that.
weird.
And I was like, is this DHEC? She was like, it's across the street. And I was like, I apologize.
Old people saying that like that, like excuses.
Yeah.
They're holding me at DHEC?
Best care money could buy, perhaps.
Department of Health and what? I forget the full acronym.
Let's find it out. Department of Health and Environmental Control.
Okay. So, talked a bit about differences in waves. Let's go back to something they all have in common. Waves are traveling energy. If something's traveling, that means it should have a measurable velocity. And conveniently, all waves, by virtue of by definition, have some velocity. And the old-fashioned formula for velocity does still work here. If you can measure the distance a wave travels and the time it takes that wave to do so, you can still do v equals delta t over delta t. That is still fine. There's a second formula, though, in terms of the wave's anatomy itself. Wave speed is equal to its frequency times its wavelength. I might not have specified. This inverted y is the lowercase Greek gamma, and that is the variable for wavelength. And to show why this works, oh hey, I do still have an eraser. I'll just do it over here. E equals frequency times wavelength. Frequency is measured in hertz, wavelength is measured in meters, but 1 hertz is 1 over seconds. See where velocity comes from?
Can you say all of that again, please?
Yes. So wave velocity equals frequency times wavelength. Frequency is measured in hertz, wavelength is measured in meters. This is the number of waves per second. This is the length of a single wave. Because this is waves per second, 1 hertz can be rewritten as 1 over seconds. By definition, 1 hertz is 1 over 1 seconds. Therefore, 1 hertz times 1 meter is 1 inverse seconds times 1 meter, meters per second.
And what did you say that symbol was?
Oh, this is lowercase gamma.
Is that not lambda? I always thought that was lambda.
Oh, it might be lambda. Hang on. I was never a Greek scholar. One sec. Oh, yep, I've got it wrong. That is not gamma. Lowercase. Yep, that's a lambda. Or it will be a lambda.
It looks like the bolt in the
That's a
back.
lambda. Sorry, you were saying?
It looks like the bolt in the trash. in SpongeBob.
I remember that episode, but no one has ever told me that's how one should remember lambda. Okay, so all waves have a velocity, they all have a frequency, they all have a wavelength. As I attempted to demonstrate with the slinky, a specific type, why did I put the eraser back there? A specific type of wave in a specific type of medium has a specific predetermined speed. Some constant speeds that do come up repeatedly. Speed of sound in air, specifically room temperature, sea level air, is 343 meters per second. The speed of sound in room temperature atmosphere water is about, I don't remember this one precisely, 1,500 meters per second. And speed of light, which has its own variable, actually. You ever see a lowercase c in a formula? That's the constant for speed of light. And subsequently the speed of all of the members of that electromagnetic wave family is 3 times 10 to the 8th meters per second. Notice a difference in magnitude in any of these.
It's faster than water than the air.
Sound is faster in water than in air. It's even faster in solids. The exact speed in any given solid will depend on the solid, but as a general rule, sound travels faster through denser materials. Meanwhile, light is literally the fastest known thing in the universe.
They don't care about any material.
It does not. We consider light's speed to be a fixed constant anywhere. Through the void of space, through air, through water, we consider this to be the speed of light, period. One of the fundamental queries and also constants that we have based most of our math around is the idea that this number will always be the same, no matter where you are. And since the velocity term of this formula is basically capped for all of these wave types, depending on what it's traveling through, that means adjusting the frequency of a wave will adjust its wavelength, not really its velocity. If the velocity is constant, changing one of these two things will only change the other one. Yes?
So if you're in a spaceship and you're going the speed of light
Okay.
and you turn on a flashlight, would it not turn on or would it turn on? Like, would it go like, or would it like just like look like it's off?
You would theoretically be traveling at the same speed as the light you were making. So it would be like if the flash threw a rock and then ran alongside it as it flew.
So would it matter that you were in the spaceship and the spaceship wasn't moving on the inside?
See, this asks way more questions than the ones that you're already implying, because we don't know what human beings are like or can perceive at that speed, let alone how the universe behaves. You might not perceive anything, frankly, because at that speed, you'd be the same speed as all the light around you, meaning none of it might actually enter your eye, meaning you might not be able to see anything.
Okay. That's a good point. What if the flashlight was facing the opposite direction?
Then it would be moving away from you at double light speed.
Now that's speed.
And we don't know, I don't know what effect that would have on, like, have you guys heard of the Doppler effect? After talking to my other lecturer, it sounds like it came up last semester. If the thing creating a wave or the object that it echoes off of is moving, that changes the wave's frequency. So if you got in a spaceship, you were looking at a green star, and you started rushing towards it at a measurably fast speed, it might not look green anymore.
Interesting.
But I have no idea how moving at light speed would shift the frequency.
So could everything be different colors, like if you're moving at light speed?
If it's even visible light anymore, you might shift it into gamma territory and burn your eyes out.
I'm pretty sure that your retinas and the mechanisms work, they only work at like a 10 to -2 per second speed. Like, they don't work that fast.
You're right.
Okay, so what if you weren't going light speed, but you were going really fast? Could you make stuff change color?
Yes.
Really?
We track how fast some stars are moving by the frequency shift of their colors.
Interesting.
That's cool.
because that far out, we don't really have depth perception. We can only tell if something's moving towards us or away from us based on that color shift. It's kind of like how bats and dolphins can echolocate, and bats and dolphins know what frequency of sound they make. And when they get sound back, they not only measure, okay, that took 3 seconds, so it's X feet away from me, but the frequency changed, so if the frequency is higher, they know it's moving towards them. If the frequency is lower, they know it's moving away from them.
So how do we get pictures of stuff like in space? Are they fake pictures?
No, they're real pictures. Like, light is traveling towards Earth.
But like when we have those really detailed pictures
Of what?
of like galaxies and stuff.
Those tend to happen by facing a camera towards something and leaving it there for a long time, collecting as much light into the lens as possible.
How do we have pictures of our own galaxy right now?
Hubble telescope.
But it's also in it.
Okay, we don't have a picture of the entire Milky Way. I don't
But
think.
then how do we have pictures where it's like, you are here?
A lot of those are probably artist reconstructions.
Fake pictures.
We have aliens sending us pictures.
About time.
No, we have to pay an intergalactic subscription fee to get these academic photos from planet Andromeda.
The stock image logo.
There is actually a stock image logo, but it's in a language that none of us can comprehend with our human eyes, so, can't see it.
The proof pics that you got in like middle school or whatever.
Okay. Using these numbers as constants. Quick sample questions. What is the frequency of a 10-meter wavelength sound wave?
What is that number at the end? Oh, is that a different question?
Hmm?
Never mind, I'm good. Is it
Yes.
in air?
Sorry, yes, in air. The human ear was designed for air, so we're going to stick with that for now.
Does it 10 to the negative 5?
It does, 10 to the negative fifth. How would it feel? There's not a lot to this particular formula, so this is just practice, rehearsal. I don't know. Frequency of 10-meter wavelength, sound in air. Sorry? I didn't hear what, I heard someone say something, I just didn't hear what.
My calculator is dead, so what's the answer to the 1.0 times 10 to the negative 5?
1, 2, 3, 4, 5.
Yeah, that's what I thought.
34 million. Yes. So for context, you would never hear this. You know how there's sounds dogs can hear that humans can't? Dogs can't even hear this.
What can dogs hear? Up to, do you know?
Yes, actually. This comes up often enough in my examples that I have these numbers off the top of my head. The range of human hearing, maximum range of human hearing, for the healthiest possible human ear is 20 hertz to 20,000 hertz.
Hey, we ain't even close.
Correct. Dogs take those numbers and double them. 40 hertz to 40,000 hertz.
Hey, ain't even close.
So any dog whistle likely operates at about 30,000 hertz.
Do you know why or no?
Why what?
Why they can hear better?
Oh. Well, probably has to do with like our functions on primeval Earth. Like, there's not really any sounds above this that a human would need to perceive. Like, we're used to interacting with each other, and no human voice really goes over 10,000 hertz.
Attack dolphins?
Attack
Honestly,
dolphins.
look, bro, if I'm swimming.
Well, since we don't live underwater and we don't have to deal with attack dolphins, we have not. Our ears are not designed.
Attack bats?
Attack
That's how
bats.
Atlantis fell.
Well, bats themselves are not much of a. A single bat is not really a threat to a single human.
Flocks of vampire bats?
Well, they don't go after human blood. They're also like the type of bat that eats blood is like yay big.
They're kind of cute.
It can be. I prefer the flying foxes though, which are
The
like
fruit
The
bats?
what?
Like Stella Luna?
don't know about that one.
Oh, it's a book.
Actually,
Why?
vampire bats and fruit bats are in the same family. They're basically mice with wings. There's two types of bats: mice with wings that eat fruit and or blood. Then there's the flying
Hey, fruit
foxes.
bats are big.
Hmm?
Fruit bats are big.
Well, the mega bats do eat fruit, but there are tiny fruit bats as well. Not all tiny bats drink blood.
Excuse me, this should not be allowed. Why is it so big?
Let me see.
They call them flying foxes for a reason.
Largest creature.
Yeah, it's like Stella Luna. Look up Stella Luna.
What was I saying?
The last one. How do you do the last one?
Ah, this isn't actually a V equals frequency wavelength question. This is just a V equals D over T question. Whenever you see lightning, the light is so fast it travels from the lightning to your eye basically instantly. Like, light is about 1,000,000 times faster than sound.
Is that an S or a 5?
That's a 5.
Oh, that makes a lot more sense. I thought it was an S also. I was like, why do you write it twice?
Sorry.
I mean, but it's 5.
Yeah, very clear.
So, light, same formula as above. Don't actually have that number. Big number. So that particular frequency of light would be about 5.5 times 10 to the 14th hertz. That's roughly 55. No, I think it's 500. I think it's 545 terahertz. Yep, no, I can write wrong. And then I stepped on my cable again. That's 545 terahertz. Which
Is that
No, actually, it's green.
Green.
Dead middle of the spectrum.
Those are pretty close to the same thing, I'd say.
Okay.
And then the thunderclap. Every lightning bolt you've ever seen, the light is so fast, we consider it to instantly get to your eye. Like, that's faster than the human brain can process. But since the sound is measurably slower, that's a slightly more reliable measurement. If you count the number of seconds between the lightning bolt and the sound of the thunder, you can get a pretty good idea for how far away the lightning strike was. If for some reason they both happen at the same time, that's because you're the one who got struck by lightning.
At least you can do the little counting thing, but I don't really have a concept of distance, so it would never really be useful.
Did Mel Gibson get struck by lightning?
I don't think so.
Oh, he's fine. I'm pretty sure he did.
Mel Gibson.
Yeah.
Is that
I want
part
to
of
say like he was filming a movie and he got struck by lightning.
That's what you get for just raising your claymore too high on the set of Braveheart. This third one here is sort of symbolic as to how to look at echoes. It takes an echo a certain amount of time to travel from the source to wherever it bounces off of, and then it takes the same amount of time to get back. So this trick is useful for figuring out where the lightning struck. It's similar to how to work an echo question, except for the case of an echo, you want to cut the time in half. Because if you scream into a cave and it takes 2 seconds to hear your echo, it only took 1 second for the sound to hit the cave wall and another second to get back to you.
Interesting.
Yes. I want to look briefly back at this. Come on. This is the frequencies and wavelengths of light the human eye is capable, that most human eyes are on average able to see. Any other frequency of electromagnetic radiation entering your eyeballs won't trigger the photoreceptive cells on the back, so you won't trigger a sight response. Similarly, why did I roll this down? I was just going to roll it back up. Any sound above or below this range that enters your ears just won't do anything because your system's not designed to be able to handle it. Humans can hear this range because these are the sounds that humans are most likely to encounter while speaking to each other and dealing with the normal noises we encounter in our daily lives. Most animals tend to have a higher range because if you're in a hunt or be hunted situation, you need to be able to hear every possible noise the things trying to eat you can make, which includes every single blade of grass rustling under their feet. However, there are a few sounds humans can hear that dogs can't. Really, really low sounds that we'd never encounter, but we could. If we wanted to make a human whistle, make it 30 hertz. Lastly, this number right here, the 20,000, I guarantee none of us can hear that.
You have it on, can you look it up on your computer for the sound?
Yes, actually, I was about to. None of us can hear this, because this, if you're lucky, is the maximum frequency you could hear the second you were born. Every moment that the cells of your eardrums are alive after this point, that number drops as your cells age and divide. And it drops faster when I blast sound directly into my ears through earphones. If you don't take care of your ears, this upper number declines faster. And there are, if you go on YouTube and type in sound test,
Isn't there supposed to be a frequency that like makes you study better?
I don't know about that.
Where are the weeks in the bottom of this shit?
Paris, I just want to know where you're hearing all this stuff.
I swear, and they like will make music, but they'll have like I think it's like 110 or something, and they'll make songs that have it just in the background, and you're supposed to study to it because it makes you smart.
Blocking my hidden potential.
Look up study frequency. That's what I do.
Okay. This is a hearing test, is actually what they're called. These things are all over YouTube. This just runs through every possible frequency that a human should optimally be able to hear. It's coming out of my laptop speakers. So it's not going to be very powerful. These low frequencies are hard to hear for anybody, but you can hear them.
Surely there's no sound right now.
No, there is.
Well, now I hear it.
So these low frequencies, 300 and lower, are bass tones. And if you look at the math, if frequency is small, wavelength is big. So these sounds, we can technically hear them, but you're more likely to feel them. Because when a big bassy wavelength hits your body, you feel your bones rattle more than you hear your eardrum vibrate. Which is why cars with their bass turned up tend to make every part of your body shake. Meanwhile, the frequencies get higher. I'm going to skip through a few of these.
I don't get so scared when he gets this stuff with people.
That's fair. Because frankly, these sounds are all alien. No sound you will encounter in nature is any single frequency. These are all single tones, but any human voice is multiple frequencies layered over top of each other to create a more complete sound. We're not used to this, neither are dogs, frankly. It's literally artificial. That's probably why it's so scary to them. But these tests will keep rising. This is usually the maximum, about here is like the maximum that any human voice would be made of, or any part of music might be made of. And yes, it's going to start getting really even more annoying.
Yeah, let's get to the part
What's
right
the
here.
maximum humans can hear?
A newborn baby, 20,000. But we're getting to the point now where once you stop hearing it, raise your hand.
Please, God, let me stop hearing this. Okay, I think we're there.
Ooh. You guys have really healthy ears.
No,
So-
never mind. I wasn't hearing it.
The air?
I was not hearing it. No, they're not.
Okay, Jess, go on.
No, I'm. Oh my god.
So the older you get, that top number should drop. So you guys should have healthier ears than me, even before we factor in all the loud music I've had. That said, you can pack up and go. I just find it interesting that this is probably one reason why the old and the young will never agree on music. But both the elderly and the youthful have figured out how to weaponize this quirk against one another. Grocery stores have started playing very high frequency sounds outside their doors so that the kids loitering outside are constantly being bombarded with high-pitched noises, but the adult paying customers aren't.
Sounds funny.
Wow.
Kind of smart.
I
Yes.
hate this generational warfare, and I will fight against it.
But the kids are fighting back because some students have made their ringtones super high-pitched noises that they can hear and their teachers can't.
Here we go.
Whoa, that's crazy.
I'm smart.
No more getting letter grades off in Harshaw's class. Alright, see you in like 10 minutes. That's all going.
Groovy.
Maybe I'll go to the pod. Do a little snack.